All right, I'll begin with a word of prayer. So I get up here. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you could help us to use this time wisely, understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. So you guys have any questions before I before I get going here?
Yes.
Oh, I heard a yes? All right. Uh-huh.
So when it says d squared y with dx squared, like I looked up how to do it, but it was the first time I see it done.
Sure, we can talk about that. So how do you calculate d squared y dx squared in parametric context, right? All right, so first of all, I would remind you that we learned before that dy dx, if we write it as a function of t, we can do that as dy dt divided by dx dt, right? We did that before. So it's helpful to look at this in a slightly different way. What we really have is 1 over dx dt times d dt of y, right? So if you look at it that way, you can kind of gain a sense of what we want to do for the second derivative. So for the second derivative, d squared y and dx squared, what we want to do, if we want to look at it as a function of t, then we're going to do 1 over, well, my bad, one more step here. So that's really d dx of what? Of dy dx, right? And you're looking at that as a function of t. So to do that, what we do is 1 over dx dt times d dt of dy dx. And to be clear, I don't know how much, let me just leave it like that. I mean, technically that's a function, everything here is a function of t, all right? Now, there are different paths you could go down here. One thing you could do would be to go, well, we already know what dy dx is, right? In terms of time derivatives, it's up here. I could rewrite this, right? This is really y dot over x dot if we use Newton's notation. And so what we're looking at here is 1 over x dot times d dt of y dot over x dot. And then so you got a quotient rule, right? So that's 1 over x dot times, well, what you got? You got yourself a x dot y double dot minus y dot x double dot divided by x dot squared. So you can derive this simple, well, simple, I don't know if simple is the right word, but straightforward formula, x y double dot minus y dot x double dot. It gives me joy to say double dot. Anyway, so then x dot cubed down here. So here is a straight formula for calculating the second derivative of a function of x, parametrized as a function of t, to calculate d squared y prime prime as a function of t in terms of the time derivatives of the parametric formulas for x and y respectively. But pragmatically speaking, it is often simpler to simply use this formula right here directly. So I would say you could use this, or you could use this. It's kind of a matter of preference. I think in terms of you guys, since I don't give you a sheet of notes for the test, right, you have to remember some things. I would tend to prefer this because it's easier to remember this. Basically, you just do it the same way as you did before. It's just, it's a two-step thing. So use this one, plug it in here, right? So this goes in here. Let me actually do an example. What's our interest in the second derivative anyway? Why do we care? Yeah, concavity, right? So let's see here. Example, if I have x equals to hyperbolic cosine of t, and if I have y is equal to hyperbolic sine of t, all right, then I can calculate dy dx. What do I get? So this makes x dot what? Y dot what? Sinh cosh. So we've got y dot over x dot, which in this case is cosh t over sinh t. For reasons I don't understand, I said that that was hyperbolic tangent of t in the quiz 8 solution, which is just nuts. That's of course not hyperbolic tangent. This is hyperbolic cotangent, for what it's worth. But probably you just want to leave it as cosh over sinh, because how many of you know the derivative of hyperbolic cotangent with confidence? Yeah, I saw a half of a yeah. So you're going to end up differentiating hyperbolic cosine over hyperbolic sine anyway. So let's do that. Okay, so d squared y dx squared, how's that go? All right, so we're going to do 1 over x dot times d dt of dy dx, right? I'll write this symbolically down here. And then what is that? Well, that's 1 over sinh t ddt of what? Well, cosh t over sinh t, because we agree that we don't remember the derivative of hyperbolic cotangent, apparently. I mean, I don't, admittedly. But I do know the quotient rule. So I think we'll be okay. So I do derivative of the top, which is sinh, times the bottom, which gives me a sinh t. And then I subtract the top times the derivative of the bottom, which gives me a cosh squared t. I divide by sinh quantity squared. And so then you guys know your, whatchamacallit here, the your identity. What's the identity at play here? It's 1? It's negative. Is it 1? Is it negative 1? What do we want? Negative 1, right? It's easy enough to remember that. Try plugging time is 0 into this. What do you get? Sinh of 0 is 0. Cosh of 0 is 1, so you get minus 1. And this is a constant, so it's minus 1 everywhere. So you get minus 1 over sinh cubed t. There it is. Now, alternatively, right, you could use the boxed formula. How would that go? X dot y double dot minus y dot x double dot divided by x dot cubed. Let me do some things up here. This is actually equal to what? What's sinh t equal to? It's y. What's y dot equal to? It's x. So what's x double dot? What's y double dot here? It's, yeah, x and y respectively. So this is literally y minus x divided by y cubed. But as you can see here, y squared minus x squared is 1, so you get minus 1 over y cubed. I mean, anyway, I'm playing some games here, but you see you get the same answer. But you notice the difference. Here I didn't have to do the quotient rule because the quotient rule was done for me in the derivation of the boxed equation, so, you know. Yes, sir?
So, like, we had that on, like, a test, and you said determine the concavity.
Mm-hmm.
How, like...
Oh, yeah, I haven't figured out the concavity yet, have I? So for this one, what can we say about concavity? Concavity, remember we have this characterization theorem, if you will. If y prime prime is greater than 0, then, you know, concave up. If y prime prime is less than 0, then concave down. Now, technically, it's always on some interval, right? So we talk about concavity, we talk about increase and decrease on an interval, right? Not at a point specifically. I mean, we can test the calculus thing at a point, but really, geometrically, do you guys know how to define concavity without calculus? What's that?
Whether it holds water.
Whether it holds water. Fine. I was looking for math, but you're not wrong. So he says it holds water, right? Can you guys think of another definition that doesn't use water? Or other liquids? Yes? There's points, and there's the line, and there's a lower tangent. How about, I'm going to stop you right there. Points in a line is enough. So to say that this is concave up means that if you draw the secant line between any 2 points that connect the graph is below the secant line. The secant line is just this guy. So if you can do that for arbitrary points in the interval, then it's concave up. If the secant line is always above the graph for arbitrary pairs of points, which I think is what you're saying. Right? But it could be also like this. You know. Anyway, all the different if the graph's always below, and in contrast, if you're concave down, you draw the secant line, the graph is always above the secant line, right? And there are infinitely many different secant lines to consider for a given interval, right? It's very cool that we don't have to think about this, that we can just think simply about the second derivative being positive or negative to capture concavity. And a lot of calculus books will just make this the definition of concavity. But anyway, so you guys tell me, this curve, where is it concave up, where is it concave down? So it should be concave up, where what? Concave down, where t is what? So we want the second derivative positive. What's the graph of sinh look like? Do you guys know? What's that? Like a cubic, I think is a good answer. Like that. The difference between it and a straight cubic, there's a couple things. Number one, it goes through the origin with slope 1, because the derivative of sinh is cosh, and cosh of 0 is 1, so it's slope 1 at the origin. And the other thing is that this thing has exponential growth on both tails. So if you were to really look at it from the larger scale, you'd see that this beats the cubic a lot if you get further out, because it's got exponential growth both ways. But that is all I need. So you can see sinh is positive, sinh positive over here, sinh negative over there. So what's the answer? Concave up for my example. T less than 0, it's concave up. T greater than 0, it's concave down. Right, because the minus sign here flips it. Does this make sense? What graph are we looking at? I did what? I've got x equals cosh t, y equals sinh t. What is this? This is x squared minus y squared equals 2? What? 1, right? This is a hyperbola. I sometimes call this the unit hyperbola. It's got asymptotes of y equals plus or minus x, like so. And what we are looking and studying here is the right branch of it, right? So you got this piece here, and you've also got this piece down here, right? So down here you've got t less than 0. Up here you've got t greater than 0. As you can see, concave down up here, concave up over here. Although, if you want it to hold water, it's just change gravity. Give it a strong wind from that way or something. I don't know. So, yeah. Yes, sir?
When, like, I think there's a question on the homework, and it was determining concavity, and it was an ellipse. Is that just like determines where the t's at, or because like you're just going based off the x value, just concave up and concave down.
Yeah, so I mean, you'll have the second derivative as a function of t, so then the question becomes, where is that second derivative positive, where is it negative?
Okay.
It depends on the formulas. But of course, you can go back to x's and y's and graph it and pretty much easily see. I mean, if you give me an ellipse, I can tell you where it's concave up and concave down, right? Like, but the analysis for t, though, should reflect this, yeah? Mm-hmm. So if that's the dividing line, it should be concave up down here, right? It should be concave down up there. We're not like the physicists insist on having concave and convex. We just have concave. Aren't you happy? We have no? Oh man.
We don't have the right concave down or concave up. It'd be concave or convex.
Hmm.
He has a point.
Hmm.
Less writing, you know?
But we could have concave up, concave down, and then convex up and convex down. And then convex down would be concave up. And convex down, you say convex is just a cool word? Well, agree to disagree. Let's see here. I'm sorry, what am I saying? We don't agree to disagree anymore. Either you agree with me or you're a racist. So that's how we do it now. But or a bigot, or you're afraid of whatever form of debauchery is the current, you know. Current rage. Anyway, other questions? I think I've answered your question. Okay, yeah.
Is the x dot just derivative of x?
Oh yeah, x dot is just dx dt, and x double dot is d squared x dt squared. So this is old notation. This is Newton's notation. The dy dx is Leibniz notation. It's like both Newton and Leibniz discovered calculus about the same time, and they had really different notations for it. And guess who won, notationally wise? It was Leibniz won, right? Because we don't use these dots that much, except in physics, right? Yeah.
So for the y minus xx, the first, yeah, did you just like plug in to get -1? Like,
Well, y squared minus x squared is, again, it's the same thing as here.
right, so that's how you got that. You didn't, like, that's not like an identity.
It's only an identity because we're using constant here, but yeah, generally speaking, it's not. Unless we're dealing with polar coordinates, in which case it's equal to, well, it's still nothing. But if it was x squared plus y squared, it'd be r squared. Yes, sir.
So over here when it gives the d2y over dx squared, why can't you, kind of the same thing we did up top where we did dy over dt over dx over dt, why can't we do like the second derivative of y over the second derivative of dx?
Because it actually works out to that.
Oh, they both actually work out the same thing?
Well, I mean, it's just not equal to that.
Yeah.
This shows that it's actually this. So, I mean, it's not y double dot over x double dot. I think the answer really is that, I mean, you are differentiating a quotient is the thing.
Yeah, 'cause
The-
like
the-
one,
the reason-
one-
The reason we had this, remember we looked at the velocity vector and we had, we could identify the x and y components respectively as like rise over run, and they're also dx dt and dy dt. I might have flipped which is rise and which is run in that sentence, but if you looked at the acceleration vector, it's well, that's the question is, I don't know if we've ever really thought through this. So I know what the acceleration vector is, right? So if I start out with r, position, I've got x, y, right? I mean, what you're asking is a good question. I think to give a full answer to it, it requires perhaps about 10 minutes. X dot, y dot, right? dx dt, dy dt. The acceleration is x double dot, y double dot, right? But what is the second derivative geometrically?
Is it not the rise over run of the y and the x, the second derivatives?
The rise over the run.
Can we not do the same thing we did for position to velocity?
I don't think so. I mean, I know we can't because that's the answer, but I'm trying to think of how to explain it.
Because I get why you take the d dt of y and then you divide it by dx dt, but because of dy dt over dx dt, but I don't get why you do it again in the second derivative for not using that like same dy over dt, dx over dt technique.
Well, it's because the derivative of that fraction isn't just the derivative of the derivative.
Yeah, I mean, the idea is that we're doing the same thing as we did up here to dy dx. So, yeah.
The thing is, so when you find a double derivative, you're finding the rate of change of the rate of change of y with
Mhm.
respect to the rate of change in x, not the rate of change of the rate of change in x.
Mm-hmm.
It's all versus like the change in x, not versus.
Yes. Yeah. Yeah. I mean, I think you're right. But the question still remains: why isn't it just given by? Why isn't that just given by x double dot divided into y double dot? Right? I mean.
Because x double dot would be like the concavity of x versus t, not just the change in x versus t.
Mm-hmm.
Which is what you're trying to find, the concavity of y versus, basically.
I think that's about right. I'm trying to think if I could. I think if we looked at a specific point, we could look at the tangent line to the point and sort of replicate the argument for the y as a function of x for the tangent line. But the tangent line doesn't just involve, it involves the x dot and the y dot is the thing. Anyway, I don't know, I think what Caleb said is like the best, is probably the answer you're looking for, but I better stop there because I have other questions. So I don't think I have anything more to add here at the moment. So yeah.
So we know the arc length for in terms of Cartesian, but not necessarily in terms of polar, if that makes sense.
Oh, wait, I wrote the formula down for arc length in terms of polar last time, though. So it was to calculate, if you have a polar graph, the formula for arc length is you integrate the square root of the radius squared plus the derivative of the radius squared with respect to theta over theta. Or if you have a polar parametrization, you calculate the square root of r dot squared plus r squared theta dot squared, square root of all that times dt integrated over the appropriate range of time. Like those are the two formulas to think about for polar coordinates. Both of those ultimately stem from the fact that the speed in polar coordinates is the radial velocity squared plus r squared times the angular velocity squared. But I mean, I can write that down. But so S, now the problem you're thinking of, is it like r is a function of theta, or is it r and theta are both functions of t?
Yeah, it's a function of theta.
So if r is a,
There's
1 plus sine theta. So we integrate from like theta 1 to theta 2 of the square root of, r squared plus dr d theta squared was what we found. So you just basically, you'd calculate the arc length like that for your specific r. Hopefully, well, if it's from the book, right? It's from the book, yeah? Then that square root will magically become one of the ones that you can do. Other questions? Let's see here. So I was going to try to work some problems here for you. Example, where am I? What example am I on? I've lost track. Was this example 2?
Yep.
Okay. Yeah, I can't stop thinking about this one. I think ultimately the answer is that x and y are not the same here. All right. x and y are not the same. Like x is the independent variable, whereas y is the dependent variable, and their roles are different. That's why there's an asymmetry. It's a fortunate thing that we can calculate dy dx as a function of t just like that. But anyway, I should shut up. Let's see here. I tried to take a picture of some area between polar curves problems from my other book. Hey, wait a minute. Stupid phone. Too smart. Flip back. Go back. It was big a second ago. Curses. All right, so we're supposed to find the area between two curves. Find the area of, so I'm looking at r equals to 2 cosine theta. Sorry, just a second here. I gotta, oh man. My phone has clipped out the sentence. We'll have to do some imagination here. Imagine the rest of the problem. So we have r equals 2 cosine theta, but outside the circle r equals 1. So I think I'm missing like a word or two outside r equals 1. So can you guys, come on, phone. So outside of inside of r equals 2 cosine theta, outside r equals 1. That's what the problem is. All right, so inside this, but outside that. We want to find the area of that region. Can we make sense of this? What do these look like? So with a problem like this, a large part of the difficulty is just figuring out what the graphs actually look like, right? So for my money, when I've got something like r equals 2 cosine theta, for me the easiest way to proceed is algebraically. Now you can graph it if you want in terms of that scheme we had, but what I'm going to do is I'm going to multiply this by r, and I get r squared is equal to 2r cosine theta, which gives me x squared plus y squared equals to 2x, which gives me x squared minus 2x plus y squared equals to 0, which gives me x minus 1 parentheses squared plus y squared equals to 1. So from this algebra, I learned I'm looking at the circle of radius 1 centered at 1, 0. And then I can make sense of the question. So let's see here. So that's my circle, right? And what's the other circle at play here? Radius 1, right? The unit circle. That also is going on here. So that's a point on the unit circle, actually, right? I tried anyway. So there's your unit circle. Now, let's look at the problem statement. Does it make sense what's being asked? We're supposed to find the area. I'm missing the words find area. Find area inside r equals 2 cosine theta, but outside r equals 1. Where is that? All right, so if I go out from the origin here, right? Like that. We're talking about outside of the blue circle, but inside the black circle. So here's like some typical points right in here, right? So if I was to shade the region that we're trying to find the area in, it would look like this, right? This guy. We're trying to find that area. So what's the inside radius? What's the outside radius? You can see that the inside radius is, it's the blue circle, right? So it's 1. The outside radius is what? It's given by the other one, right? Which is what? 2 cosine theta, right? Is there, yes, sir?
I'm confused about the step. When you said r squared is equal to 2r cosine theta, and then you made it to x squared plus y squared equal to 2x.
Oh, well, I'm still using the polar coordinates. You must remember these. So we have x is equal to r cosine theta. Y is equal to r sine theta. So this means, among other things, that x squared plus y squared is equal to r squared, and a few other things, but that's what I've used here. So r squared was x squared plus y squared, and yeah. You could also use the graphing technique that we talked about the other day to graph this if you didn't see this algebraic root. After you do about 3 or 4 of these, you start to see them coming, all right? So, all right, so great. Now, if you look at this, you see what's going on here. You've got this point and this point. These, oh, I tried. Oh well, try it again. Ah. You get the idea. So this is theta max. This is theta min over here, right? And you see that basically we're going to sweep from here to here to get that area. So what angles are those? How do I find those? Those are where what? Yeah, that's where 1 is equal to 2 cosine theta, which tells us that cosine theta is 1/2. Let's see here. So if I graph my cosine like this, right? Cosine equal to 1/2, it's about like here, right? So of course we have theta equals to pi over 3 is one of them, which is obviously this guy, right? And down here, you got minus pi over 3, right? Because it's clockwise. And that's the solution, right? And definitely we'd like to use, I think it's pretty clear, we should use minus pi over 3 less than or equal to theta less than or equal to pi over 3 for this integral that we're going to calculate to describe the area, right? Okay, so based on the thing I drew last class, remember in terms of the sector and the fan picture, the area is the integral from minus pi over 3 to pi over 3 of 1/2 r out squared, which is what? 2 cosine theta quantity squared minus r in squared, which is, well, 1 squared d theta. So before we do this integral, do you have any suggestions about how we can make our life easier? Any kind of obvious simplifications for the integral here? Anything integrate to 0, for example? I think no, nothing integrates to 0 necessarily. Yeah? Oh, but there's a 2 there. But there's a 2. I mean, I do think we are going to need the half angle identity to integrate cosine squared. That's true. But what I would point out here is there's a symmetry, right? From the original picture, the area above is equal to the area below, right? So we can just double up from 0 to pi over 3. And I don't know about you, but I much prefer to have one of my bounds being 0, right? As opposed to minus pi over 3. So we can trade this half times 2 for just 1, and we're just looking at the integral from 0 to pi over 3 of 4 cosine squared theta minus 1 d theta, which is, of course, the integral from 0 to pi over 3 of, well, this is going to give you a 2 times 1 plus the cosine of twice theta minus 1 d theta, which is equal to the integral from 0 to pi over 3. 2 minus 1 is 1, so you get 1 minus twice cosine 2 theta d theta also known as theta minus the sine of 2 theta. Evaluate that thing from 0 to pi over 3. You get yourself a pi over 3 minus the sine of, well, 2 pi over 3, which is, let's see here, draw my graph. So sine of 2 pi over 3 is about here. I think that's root 3 over 2. So I think we get pi over 3 minus the square root of 3 over 2. I could be wrong about the root 3 over 2. I'll have to check on that. Curious. I got a sign error in here somewhere. Where did I do it? Oh, duh. Come on, guys. You guys can tell me. Where's my sign error? It's kind of obvious. It's 1 plus, yeah. So I don't know. This is magical. Like, this plus just becomes a minus because I moved it over here, right? It's sad that I moved it. It became unhappy. That's a plus. That's a plus. And this is approximately 1.91. So there you go. But yeah, that's it. Yeah.
Can you explain again how you get that R outside P2?
How I got what?
The top, like the R outside of 2.
Oh, this here?
No, sorry, like the top of the board.
Oh, this? That's the
No,
problem statement.
The blue, the C R in equals 1, like more to the right.
Oh, from this picture. So the inside radius. So as I look at anything going out from the origin, as I'm trying to set up the area, I have to identify going out from the origin as I do that, right? Let's do this blue ray here. So if I, blue ray, if I take this and I go out like that, the first thing I hit is R equals to 1.
Yeah.
And then I'm inside the region I'm finding the area of. And then I hit this. So this is my R out. And this is my R in, which respectively is 1. And the other is 2 cosine theta. How do I know it's 2 cosine theta? Because I derived it from here. So that's how I knew that. I mean, this is the problem of setting up the area of a polar region, is you have to come to an understanding of what's the inside radius, what's the outside radius. Come on, phone. I'm trying to find another problem here. Does that make sense? Or have I answered a different question that you're not asking?
Kind of. So you're just saying because that's like the outside radius.
Yes, because that's the outside radius. Yeah.
Professor.
Yep.
Isn't this question kind of just a calculus 1, like washer method question?
I don't think so, because it's not a volume. We're calculating an area here. I mean, there may well be a related volume problem, and it's possible. But for example, this is the volume. If you take this and you just think of these as flat potato chips and make a stack of them one high, that's the volume of such a region. I can always take any area problem and just make it thick to make it a volume problem. Hey. Yeah. Yes, sir.
I know sometimes with integrals you have like signed area that you have to make an absolute value of. Does it ever get messy with the radius being negative and there being signed polar area?
Yeah, I mean, we have to watch out for that. I would try very hard to characterize the area I'm looking at in terms of positive radius, just to not go nuts. A lot of times the problems that involve negative R, they're very symmetrical, and you can just focus on the part of the shape that has the positive radius. like for example, this problem. Find the area that is within one petal of r equals to cosine 3 theta so find area inside one petal, but there's a string attached here, but inside the radius 1/2 circle. So let me see how much time I have. Okay. So I'd like to, I mean, it would be lovely if I had about, 5 minutes to slowly explain how to graph r equals cosine 3 theta. I'm going to have to do it a little bit faster. So what's it look like? Let's see if I can do it. So here's my r. Well, I'm going to graph r and theta here. Cosine 3 theta, it looks something like this. Now, when 3 theta is equal to pi over 2, that's my first 0. So that's pi over 6. So this is pi over 6. This is minus pi over 6. This is when this is when you have 3 pi over 2, you're plugging it in. So that's actually giving me theta equals to pi over 2 apparently. So here's pi over 2, right? And if I kept going, what's this going to be over here? This is pi over 3. So pi over 2 plus pi over 3, whatever that is. All right, so getting to the point, the graph looks something like the following. So we've got, here's my pi over 6, here's my minus pi over 6. There's another one of these deals happening at pi over 2, I think. Feels wrong. Huh. Oh, this is where the negative r is getting me. I forgot about this piece right here. Where is this? From pi over 6 to pi over 2. That would be here, right? But it's negative, so it's actually down here is another one. And then the other one is over here. And here. So you got something like this. Those should all be the same. Obviously I failed, right? If I'm more careful, I draw an outer circle and make sure that my petals reach the same outer circle, right? But then we're supposed to be inside a petal, one petal, but also inside an r equals 1/2 circle. So the r equals 1/2. So the farthest these go out here is like 1. All right. This is all inside the unit circle. The radius 1/2 circle is something like this, right? So the area we're trying to find is what? We're trying to find the area in here. So inside the 1/2 circle in one petal. So in this situation, R out is 1/2 and R in is what? Right. I think my picture is not pretty enough to quite see it. If I blew it up more, you could see that the petal is more like this. And so here's the 1/2 circle. So if you look at from the, well, okay, so actually there's something, this actually has something interesting going on, doesn't it? See, because right here and right here something different happens, doesn't it? You see this? There's something going on here. These slivers are different than the middle, right? See, what is R out? Well, R in is always 0, actually. The inner radius is 0. But the outer radius is sometimes 1/2. Let me just say this. R in is always 0. It's 1/2, or what? Or it's the cosine 3 theta. So to calculate the area, I have to split it up. I need to find out what are these points right here, right? Can you tell me what those are? That's where we have cosine of 3 theta equals to 1/2, which is to say that 3 theta is equal to plus or minus pi over 3, I believe. So those points of intersection are actually theta equals to plus or minus pi over 9. So the area is equal to the integral from minus pi over 9 to pi over 9 of 1/2. What's the formula? 1/2 r squared, so 1/2 squared d theta, plus, and we can use symmetry here, right? Twice the integral, let's say from pi over 9. Why did I write pi over 2? That's pi over 9, my bad. 9, duh. So plus the integral from pi over 9 up to what? Going back to here, from pi over 9 all the way up to pi over 6. 1/2 my cosine 3 theta quantity squared d theta. That's how you would calculate the area of this problem. Part of that's easy, right? Because it's just it's a sector of a circle. So that's why we've got, this is just, what is it? Pi over 9? That just works out to pi over 9, I believe. And that one, well, you have to work that out. We're out of time, but you can calculate that, yeah. So these problems can be tricky. You have to be, so much of it is just coming to a careful understanding of what am I looking at. See, and this picture didn't do it. We could not see the nuance that we needed with this picture, could we? You can't really quite see that the outer radius. I mean, you kind of sense something's wrong, but sometimes you have to blow up and focus more on a particular region to check yourself. All right? It is, yeah, check yourself. It is tricky sometimes. Anyway, you guys, I hope you've read my announcement. I know that announcements you may or may not see, but do read that announcement I sent you guys. Thanks, guys.